بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, welcome to the second lecture in course Deep Learning or Language Modeling. And today we will have a very important lecture, and basically all the lectures are very important because they provide fundamental concept to understand how language modeling works and how we can build sophisticated language model like ChatGPT, Claude, and others. And one of the most important parts in this ecosystem is what we call tokenization. And probably you have heard about tokenization and probably you have practiced tokenization. But today, inshallah, you will discover why tokenization is really important in building a language model with high performance and how it can affect the performance of language model. So basically, language modeling, there are several parameters to make them work at high accuracy and performance. And among them is tokenization, because it represents like the foundational ground for everything else that's going to come on the top, because it's the first pre-processing step in building a language model, a large language model, or even a small language model. So the learning outcomes, first you will be able to understand the concept of tokenization and explore the role of tokenization in building large language models, including its impact on the model performance. We will compare different tokenization methods, starting from the simplest one, which is character level, and then the word level, and then the subword level tokenization, and the different techniques that we can use in subword level tokenization. And I will guide you through the implementation of subword tokenization, in particular the byte pair encoding and SentencePiece algorithms to tokenization tasks. And finally, I will show you the different evaluation metrics to evaluate the performance of a tokenizer. How can we say that a tokenizer is better than another one? Because when you build a tokenizer, of course, you will build it for a certain vocabulary or text, and then you must assess its performance according to different metrics. So before going into tokenization, let's try to localize where tokenization happens in an LLM ecosystem. So basically, tokenization is the first layer, which is considered as pre-processing layer, just after the input text. So usually in LLMs, and we talk about text-based LLMs, can also be visual LLMs, but in this case, we'll have another type of sequence. And the idea is now to convert the input text into separate tokens. So here in the simplest case, we can consider every word as a token. So it will be segmented into different parts. And there are different ways on how we can do that, because later on, after doing this tokenization, we will have every token as a single unit. And then we will have another layer, which is called embeddings. And this will be the topic of the next lecture. And basically, embedding is going to convert this text into numbers, because anything we do in a machine learning model is just a computation of vectors and matrices operations. So embedding, they will capture two types of information: the semantic information of a word, because every word has a semantic. So some words are close to each other and some other words are far from each other. And also it has to capture the position of every word in the context, because the order of words makes sense in a sentence. I mean, if you just exchange the word order, you will have a nonsense sentence. So this is what we will do in token embedding. And finally, it will go through several types of processing using different type of transformer blocks. This we will have full lecture about how to proceed. And at the end, by processing this input as embedding vectors, we will have output which will predict the next word. For example, the mouse like eating, we can have several possible tokens as a prediction. And let's say the top three are cheese, food, and bread. So all of them are viable solutions. And depending on the inference technique, you can choose either this one, or this one, or this one. And any one that you choose, it will make some sense. Okay, whether you want to have a deterministic, you follow the greedy approach, choose always the highest probability token, or something like less probability token to have more type of creativity. So this is the whole pipeline. And it turns out that how to segment a sentence into different tokens will play a very important role later on the performance of a language model, especially if we have different type of languages and different type of symbols, not only, for example, pure English words or pure Arabic words and so on. We can have different types of combinations, and the tokenizer will provide like the ground to later on understand the morphological structure of a language. So if the embedding is going to capture the semantic, the tokenizer will capture the morphological structure of a language. اسمها morphological structure. نعرف أن الكلمات it's composed of each other سواء في الإنجليش ولا في العربي. In English we can say run, running. ing form is a form of morphological structure in English. So this has to be captured in some of the ways by the tokenizer. في العربية مثلا أن الأفعال فيها جذور the roots. حتى في الإنجليزية run هو يعتبر جذر ورunning يعتبر متفرع على الجذر هذا. فنفس الشيء في العربية أن فعل ممكن صرفها يفعل يفعلن يفعلون. The tokenizer should capture the morphological structure of the language, and the embedding should capture the semantic information of the language. They have two different roles. So if we don't capture well the morphological structure, we will have trouble into even providing a semantic information to the embedding. And في الأخير, I'm not going to use words, and I will explain why. So the most logical segmentation, let's say, okay, let's divide this into words, but it has some limitation. It's possible in some contexts, but it has some limitation. So this is the language modeling pipeline. And the language model, if it is multilingual, it should also be able to provide tokenization to different type of languages, regardless of the language. مثلا هنا إذا نفس الجملة بالعربي الفأر يحب أكل. This is how we can tokenize. مثلا ال يعتبر دائما is a suffix من السوابق. A good tokenizer should understand that this a separate token and this one is a separate token. Okay, so later on we will provide it to the embedding, and finally we will have also correct predictions of what could be as the next token in this language model. And this way, this is called the pre-training phase of autoregressive models. Autoregressive models, it means they are going to learn. It's kind of unsupervised or self-supervised learning. They are going to learn from a pure input. They are not going to be supervised because we don't do any labeling here. We'll provide a certain context, and then it will provide a prediction based on that context. Yeah. This means that we're going to make a segmentation. This is like a token. Yes. No. So this is a nice visualization about how LLM predict the next word. Okay, let me just put this video. Run. So
a large language model is a sophisticated method.
This is a YouTube channel, 3 Blue 1 Brown. It's very popular. It shows impressive illustrations of several concepts in mathematics, in deep learning, in machine learning, and so on. So I recommend you to subscribe to this channel and take profit of the different visualization.
A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant. You add on whatever the user types in as the first part of that interaction, and then you have the model repeatedly predict the next word that such a hypothetical AI assistant would say in response. And that's
okay. So this is what a language model will be actually doing. It just take a context, and then will provide you the probability of the likelihood of the next token. Of course, this will be based on a vocabulary, and this vocabulary is constructed during the tokenization phase. فمش يكون فيه finite number of tokens, and this what will constitute everything that will be generated out of the language model. And this is why the data set that we will be using to pre-train the model and to pre-train the tokenizer will be very substantial later on what kind of prediction you will be having. Okay, so all is about finding the most likely token within a certain vocabulary, and this vocabulary usually is constructed during the tokenization phase.
That's what's presented to the user. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. In doing this, the output tends to look a lot more natural if you allow it to select less likely words along the way at random. So what this means is a given prompt typically gives a different answer each time it's run.
Okay, and this is why in, for example, ChatGPT and language models.
Suppose I give you two different lists of numbers, or maybe two different.
So this is why in language model, when you ask the same question different times, it's going always to generate you something different. Okay? It's not because it's reasoning, it's because it's not going to choose always the highest probability word. So every time it may provide you similar meaning, but it will be written differently. Okay? And this is because in the inference, we have a way on how we can control the creativity level of the inference. Of course, too much creativity, it can lead to hallucination. And if you put just everything greedy and deterministic, you will have always the same answer. So it's kind of trade-off that we need to do later on in the LLM inference. So the first thing that we need to understand when we do tokenization is we need to start from a vocabulary. Okay? And from this vocabulary, we need to build our token dictionary. To make things simple, for example, if all my vocabulary will be constituted from these words, okay, let's say we have a sentence, the quick brown fox is maybe running. Okay, so this is our list of tokens, and this will be our input sentence, is jumping, and we will convert it into tokens. And tokens here, you can see we have, it's, let's say, word-based tokenization, and this is a suffix. And at the end, we will have a dictionary that will represent the list of all words. And every word will just have an index. So if you imagine that this is your whole text that you will use for building a tokenizer, this will be your whole dictionary. And you will have a token that corresponds to every index. Okay? So at the end, I will consider this value index 0 to represent this token. So I can write the sentence as 0, 7, 4, 2, 3, 1, 5, 6. So this will be the output of a tokenizer. A tokenizer is going to encode an input text into a list of indices, because a machine learning model doesn't understand anything but just numbers. Okay? So that's what a tokenizer is going to do. When we build a tokenizer, it will be kind of a mapping between every token and its index. That's the result of a tokenizer encoder. And to decode, you need to take the index, and it will return back a sentence. So if I want to decode this one and recover the original input sentence, I will use a decoder that will just make a lookup table. What is this index? It's the. So this will be the beginning of the sentence. And then 7 will be quick, and this is the second word. Okay, so we will have an encoder and a decoder into a tokenizer. No, yeah, this is just, yeah, it will be during the training of the tokenizer, it will assign indices to every token. And you will see how we can do this in practice. Okay. So to summarize, we start from a vocabulary, and the tokenization, it splits the raw text into tokens using the vocabulary. Okay. And finally, it will assign an index to each token. And we can represent the sentence as a list of indices. Okay, hello world tokenization. Okay, this is how we can do it. So let's look at how tokenization works. This is the GPT 3.5 turbo tokenizer. And the tokenization, it's the bridge between text and AI, as already explained, because AI will only deal with numbers. And this is the process of converting raw text into smaller units that we call tokens. And it can be, so one way of tokenization, it's character-based tokenization. I can just take each character and I consider this is my smallest unit. That's one of the possible ways. Another way is to use word tokenization. I will consider every word, okay? And I will consider this as a token. So in this type of tokenization, this hello world, it has 1, 2, 3, 4, 5 tokens to represent a single word. And here we have only one word, okay? So if we use character-based, it will result into 5 plus 5, so 10 tokens for hello world, and here we have only 2 tokens. And subword is something in between. So it will try to capture, like, let's say, the roots of the words or the suffixes or prefixes, and try to come up with a certain subdivision based on the input text that you will provide. And the key role is to convert human readable text into a format suitable for LLM to process, and to enable LLM to process and understand the text. And look, now GPT 3.5, to make inference, when you write any prompt in GPT 3.5, tokenization like this, it will just convert this text, your text, into numbers before feeding it to the model. That's what it will do. So look, you see this one as input. The transformer or GPT-3 is just going to see this one as an input. So, and this is how it is divided. So look here, it considers token as a token, ization as another token. So why? Because this is like a suffix of several words. So the way how it was trained to extract the roots of the words and their suffixes and prefixes as different tokens to be able to construct several words from different tokens. And we're going to explain the reason behind this. Okay, so we have div, ids, the, and you can see the, it has a space here. It's with a space, input with a space, text with a space, and so on. This is the way on how it was trained.
Doctor?
Yeah.
Do you prefer any type of tokenization? For example, characteristic subwords or words? Well, it depends on the application.
Now, yeah, so in current LLM, subwords are the most efficient. These two extreme cases, they have benefits, but they have also big limitations to make good output for large language model, and we were going to explain this with all the details. Okay, so the importance of tokenization, it's central to the LLMs. Okay, it's the foundation how LLMs process and generate text. So usually this part with some LLM scientists or hobbyists, they may try to ignore it. They want to focus more on pre-training the model, bringing the data set. So if you overlook this part, it's likely you will have garbage in, garbage out, and by the end of the lecture, you will clearly observe the impact of tokenization on the LLM performance. And the challenges addressed, it will improve the handling of spelling, the arithmetics. You have also coding. Okay, when you write a full text is different when you write a Python script. So the tokenizer has to consider all these different type of situations. When you have multilingual, it's even more complex. And it directly impacts the context handling, the model performance, and also the efficiency. And the better the tokenization, the smarter the model will be. Okay, so again, poor tokenization can lead to issues like spelling errors. Incorrect token split can confuse the model, and this is something that we have experimented when we try to build some initial models. So it can generate something it looks correct, but it has several spelling errors. So of course, it can be due to text limitation, training limitation, but also tokenization can be a very important aspect that leads to poor performance. Arithmetic mistakes, numbers split into suboptimal tokens. You know, when you do arithmetics, you can do any number with any number, and sometimes a number contains only 1 digit, 2 digits, 3 digits. So the question, what is the best and most efficient way on how to should I consider them as different digits, or should I group them into clustered digits? So this is the tokenizer that will be able to manipulate this. And also difficulty of handling non-English languages, because longer token sequence could be inefficient to tokenize non-English languages. In non-English languages often result in longer token sequences like Korean and Japanese, even Arabic. I'm going to show you some examples. And also poor design of tokenization can lead to bad handling of spaces, okay, or special characters, or also capitalization. Now, egg and egg are two different words. Okay, so how we should tokenize these two words is also very important. Yeah. Yes, that's a good question. Now, what I think ChatGPT is doing in the background is trying to making proofreading. You know, there are some techniques that usually we do for chatbots, is what we call prompt expansion. Prompt expansion, one of the things is proofreading. We can proofread the prompt. We can also expand it if it is not explicit, okay? And these techniques can improve the model. And also the model could be trained on wrong inputs as well, especially in the fine-tuning phase. Okay, it could be trained because since it is trained on a huge amount of data from the internet, there should be a lot of spelling errors, and this could be one of the reasons why it can. But of course, if the spelling errors are too much, I'm not sure. I don't have guarantees that it is doing proofreading, but I guess to avoid any kind of inconsistency later on in the response. Because yes, whatever you write it wrong in the prompt, ChatGPT or large language models are able to understand the real meaning and to convert it. And it's not only this. You know that in Arabic sometimes we write Arabic sentences in English characters. Okay. Now, for example, in the Tunisian slang, we used to write in our Tunisian slang using English or French characters. And surprisingly, ChatGPT was able to decode this into the exact Tunisian slang. And sometimes I'm not able even to read these English characters as an Arabic script, but ChatGPT is able to understand. And why? Because it was trained from social media networks, where people are used to write into this strange format for expressing in Arabic. So it has learned in some of the ways. And of course, there should be also some fine-tuning, human preferences with reinforcement alignment that will help to make this model more sophisticated until these kind of weird circumstances. And this is what they make them genius. They are able to handle even unexpected situations. And they are great in terms of how general this model have become. Okay, because building generalized models is very complex. And now with the huge amount of data that they have learned, with all different type of optimizations, techniques that they have managed, these models are really brilliant in understanding any kind of situation. You can even combine Arabic with English, with German, with French, with Japanese, and it's able to grasp the whole content. It's really impressive. I'm going to stop here for prayer time, and we come back, inshallah. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so let's continue and see the effect of tokenization on using different models. So this website, you can access this website. It's called Tokenizer, and it provides you this interface with different tokenization techniques that are related to different type of LLMs. So here you can find it's the same text, input text, with GPT-2 tokenizer, which is the BPE we will introduce today, and GPT 3.5 turbo tokenizer, and GPT-4 tokenizer. So let's try to make some observations on the output of these tokenizers. So here we have an English text, an Arabic text, numbers, okay, written in بالحروف الهندية والحروف العربية, arithmetics and coding. So let's see how it is tokenized in different models. So look here, if we can see that there is probably little difference in the English, but if we look at the Arabic, there is pretty much differences here. And if we want to look at the difference, we can see the total number of tokens. Look, for the same script that we find here, the number of tokens in GPT-4 is lower than the number of tokens in GPT-2. So here, we will see this later on, that GPT-4 has made a lot of optimizations in order to improve the accuracy of their tokenizers, especially in the non-English characters and also for the coding. So look at the coding here at this space. Usually you know that there is a Python indentation and there are spaces here. In GPT-2 tokenizer, it considers every space as a single token. And this is bad in many aspects. One of the aspects is the cost. Okay, you know that if you use an OpenAI API, you will pay by token generation. Every input token or output token, it has a price. So this way is going to cost more money, okay, because the tokenizer is not efficient. And also every token generation is going to be additional execution time. So this has bad implication even on the execution and the efficiency of execution, and also will have an impact on the cost if some people subscribe to these models. On the other hand, if you look at GPT-4, and GPT 3.5 basically uses the same tokenization technique in GPT-4. It's CL100K base. So they have made such that they took into account the Python spaces as a single token. So now, in order to generate a Python script like this one, they will know that this is a single token and these tabs represent a single token. And this is much better in terms of accuracy, efficiency, and even in the learning phase, because the transformer and the self-attention module is going to try to find relationships between the different tokens into an input sequence. So if I provide this input to a transformer, it's going to get confused, because for the same text, this sequence is longer. And we have also an issue, a constraint in terms of the context length. So this will even reduce the context length. Okay, we'll have more issues and will confuse the self-attention modules in order to recognize the dependencies, because here I have several spaces that will come in a Python script. So it will be confused when to consider this as part of Python, not part of Python, and so on. However, here it's much more consistent, produce less tokens, so we have much better control of the context length in these type of situations. And you can see we have, this is the index relative to each token in the dictionary, okay? Because at the end, the tokenizer is like a lookup table and indexed with respect to its corresponding token. So I hope that this gives you some feeling about the impact of tokenization on the LLM performance, either in inference or also in training. This is just a first intuition about the fact. So comparing GPT-2 and GPT-4, GPT-2 tokenizer was trained to produce a little bit more than 50,000 tokens. So it's a smaller vocabulary, but it leads to longer token sequences. GPT-4 was trained on 100,000 tokens, which is a larger vocabulary with shorter token sequences and more efficient. So in terms of tokenization efficiency, GPT-2 breaks input into smaller chunks, which is inefficient for patterns, like for example spaces. Okay, it will consider every space as a single chunk, and also multi-digit numbers. We didn't look at the digits here. So it has, yeah. So it considers this one with the space, and here it considers the space alone. Okay, so not too much difference maybe. No, there are some differences. Like here, it has tokenized 5 alone and 42 alone, but here it considered, look, in terms of arithmetics, it was able to make a correct clustering of the digits. Here, it puts 3 digits into one cluster, and here it's not consistent, sometimes 1, sometimes 2, and so on. And context for the model performance, GPT-2 higher token counts consume context window quickly, and this limits the performance on long text. But GPT-4, it has more compact sequence, allowing better utilization of the context window. And especially that GPT-2, it has only, I think 2048 only tokens in the output. So with this non-efficient type of tokenization, it will be consumed very quickly, and this will prevent writing sufficient sequences. So GPT-4, it has better special case handling for the Python coding, combines spaces into single tokens, which reduce inefficiency, and has better handling of non-English text as well. It produces more compact tokens, but still faces dataset related challenges. And this is a summary table that will summarize all the different findings that we've talked about. Okay, now in terms of tokenization, the idea is that for every token, I will have an index. And first question maybe for people who knows about Unicode, why we don't use the Unicode encoding for making the mapping? Because a Unicode is basically a mapping between a number, which could be 1 byte, and a character, okay? Or a possible character, yes. So what is Unicode? Unicode is the standard for encoding and representing and managing text in different languages and script. Every character for every language, it has a Unicode number. And in Python, strings are considered as immutable sequences of Unicode code points. Okay, so already strings are considered as sequence of Unicode numbers, or what we call code points. So what does it mean? The letter A, its ASCII value, it's 65. So this is the Unicode number of the A. This is in Korean. It has also a Unicode value, which is 54,620. And the emoji also, it has its own code point, as we can see. So here, one of the questions, and we have 150,000 characters. So basically, the Unicode provides us a mapping between every character, multilingual, and any other number. So it could be a possibility of using this as a tokenizer, because it supports all major languages and scripts and allows representation of special symbols as well. And this is the Wikipedia page that defines and introduces the Unicode standard. And if you observe here, it's a standard that is maintained. It changes over time. Okay, so you can see back in March 2020, we had only 1,043 type of characters. And by September 2024, we reached more than 154,000 characters. So it's evolving over time. And this represents one of the challenges of adopting Unicode characters as tokenization, because it's dynamic. So if you use a tokenizer now, maybe in some point in time, it will not be able to represent all the possible type of characters for different scripts. This is one of the drawbacks. Okay, so this is an illustration in Python, how we can convert every character to its Unicode point. If we use ORD of certain character, this will give the Unicode point corresponding to the character. And we can convert all this message. So this message can be considered as just a sequence of Unicode points. And this is why the idea about why not using Unicode points as tokenizer, because what a tokenizer will do, it will just map every token to a number. Okay, here we're going to map every character to a number, and at the end we will have 150,000 characters mapped to numbers. So there are different types of Unicode encoding: UTF-8, UTF-16, UTF-32, but UTF-8 is actually most preferred. It is backward compatible with ASCII. It's efficient for most of the text, especially in English, and it's dominant encoding on the internet. So here is also some additional example about using UTF-8 byte encoding, which later on we will be using it to train the tokenizers. Okay, so the emoji will have the following Unicode point number, and we can actually use .encode UTF to get this number in hexa. Okay, so this is the integer number that corresponds to this mjoy, and this is the hexa bytes. Okay, it's encoded in 4 bytes, 240, because here we use UTF-8. So the maximum value in UTF-8 will be 256. So because UTF-8 only represents 256 values, so the representation of complex characters will take more than 1 byte to be represented. That's another issue. So now, when you get a number like this, the issue in tokenization, we don't know whether this 240 corresponds to 1 token, or I need to read it as a sequence of 4 numbers and corresponds to another token. So this is one of the issues also that we will encounter if we will use UTF-8 byte encoding as a tokenizer. Does it make sense? Okay, so Unicode treats characters as Unicode points, with each symbol having a distinct numerical identifier. Okay, look, the same one, if you use as a list, it will be represented into 4 code points or 4 numbers. And look, why we don't use 16 and 32? Because we will have placeholder will be filled in with zeros. So this is going to complicate even the tokenization issue, because it will add kind of padding into the sequence. Mm-hmm. النمبر كم مثلا يكون؟ احنا عندنا 256 كلهم consumed by the ASCII characters. Only multiple to be able to represent. Okay, فالأرقام الكبيرة هذه it will be a multiple. You cannot encode it on 8 bits. It's encoded in 32 bits. So it will be a sequence of 4 bytes in UTF-8. Okay, and this makes a challenge. And this is why now here we have the question, why not using Unicode points, code points directly as tokenizers? So first of all, we have the issue of having a large vocabulary size. That's one of the issues. And this vocabulary size is composed of characters. Well, characters, they have limitations that we will discuss when we talk about character level tokenization. The other issue is that Unicode points, they have it's dynamic standard. It can change every time, okay? So the emoji was added in 2021, and before it was not there. So if you want to use it as a tokenizer, we cannot represent Unicodes in LLMs. And maybe there are other characters that are still not represented. So this will make a limitation to be used as a tokenizer. And the Unicode, for example, in 2023 has added 4,489 new characters. And there are constant updates that disrupt the fixed vocabulary model. A tokenizer is based on fixed vocabulary. And in our case, with the Unicode code points, our vocabulary will not be fixed because it can be subject to updates. We have also inefficient sequences. For example, if you have a word like unhappy, which is composed with the prefix and the root word, it will be just represented as such. So there is no semantic meaning about, it doesn't capture any kind of semantics or morphological structure of the language. Okay, just numbers without any kind of meaning. And another thing is the context length. Long sequences of integer increase computational cost in transformer, because in our case, in this case, we will try to attend every Unicode character with each other. So, and this is one of the limitations of character-based tokenization, because we'll try to find a relationship. Look, a small sentence like this, we will have more than maybe 20 tokens. So the self-attention mechanism is not going to be very efficient in detecting the relationship between the tokens, because a transformer will not see anything about what we're seeing. It's going only to see numbers. It's like when you have an image, you know, you see this as an image, you can read it, but for a computer it's pixels with numbers, same thing. Okay, and this shares similar structure as the pixel bytes that we find in computer vision. Okay. So it's clear that we need to have proper mechanism for tokenization that yield a better performance in large language models, because we need to break the text into meaningful subword units. Okay, the LLM need to understand that there are kind of morphological relationship between the word, the characters into a certain word. So I can decompose it in this way. Okay, I can even okay, now it's happiness. We cannot decompose it in you know, but sometimes you can decompose it into prefix and suffix for the same word, and this applies even to Arabic. So the benefit of tokenization should reduce the sequence length. Okay, so a token can represent a more meaningful part of a sentence. It can capture subword semantics. That's another important aspect as well. Okay, because we don't want to consider these numbers as just numbers, but these numbers should have some semantic relationship. So later on, when we will do self-attention, this self-attention module will be able to learn these kind of dependencies. So the tokenizer would like to make it easier for a transformer self-attention module to learn faster and enable an efficient training and inference. So there are different techniques, and the most famous one is the byte pair encoding and the word piece tokenization or sentence piece tokenization. So in summary, Unicode provides a robust text encoding standard, but it's not directly efficient for tokenization in large language models due large vocabulary size, dynamic update, and inefficient sequence representation. So tokenization method like BPE provide an efficient alternative for handling text input in LLMs. Any question? Yeah.
Do we have a common case that we need just to use unicoding? Unicode encoder?
Yeah, I mean Unicode or character-based encoding, you can use it for educational purpose. Maybe when we do building a transformer from scratch, we can try to mimic a real transformer because it will be trained faster, but of course you don't anticipate you'll be having an excellent output. Okay, so for educate or for small type of problems like sentiment analysis or maybe very simple things, it could work to some extent, but it's not efficient, okay? Because still there is the challenge to understand the relationship between characters. That's the challenge, yes.
Is there any relationship between the tokens inside when we do the index encoding? Well, up until now, there is no semantic relationship between the tokens inside.
I don't say that it will really capture the semantic. I mean, the semantics will be mostly captured into the embedding layer. But it is kind of the morphological structure, okay? تكوين الكلمات. طبعا تكوين الكلمات يجي مع المعنى أيضا. لكن المعنى المباشر, it's more captured into the embedding layer. But here the tokenizer can make it easier for the embedding layer and the transformer self-attention to understand the semantics and the relationships between the tokenizer. And this is why the tokenization is actually a pre-processing technique. It's not part of the training of an LLM, but it's something that we do in advance before to prepare the terrain for the LLM later on to learn, and for the embedding also to learn better the semantics between the words. Any other question? Yes?
Is there like a certain standard for creating the index, like for example, set in
it's not like this. We use techniques like byte pair encoding, BPE, which is used to build this type of vocabulary. And even SentencePiece, it's using also BPE for merging the tokens. But there are some differences on how they consider a token representation. Okay, so let's still, although we know that's not efficient, but let's try to see why character level tokenization is possible but still not efficient. So the definition of tokenization at the character level treats each individual character as a token. Very simple. I can, and in this case, in English, I will have a very simple vocabulary. Only 26 letters will represent the whole English language. We can add punctuation digits. We can add a few tokens. It's not going to exceed something like 100 or plus 100 tokens. It's simple, and also it's language agnostic. I can use it to learn any kind of Latin language, English, French, German, or any kind of similar languages. And the use case, often this is used in early language modeling for very specific tasks like spelling correction. في عنده بعض تطبيقات لكن يبقى limited. And the process is to identify the unique characters in the data set and map every character to an index. Very simple. There is no much work to do here. So the why and the why not, the advantage is that it will lead to a simple vocabulary, compact vocabulary size, around 100 tokens. It's language independent, and also provide a fine-grained input. Okay, it can handle the out of vocabulary word gracefully. لأنه الآن, if you have the characters, you can build any word. Like if you take words, maybe you will be missing other words, so your vocabulary will not be exhaustive. So in character-based tokenization, you don't have the issue of missing words or having out of vocabulary words. But the disadvantage, every word is broken into individual characters, so this will be counted as a token. And it's the same issues that we've discussed in the Unicode tokenization. Okay, and it will also lack semantic structure. Just abstract characters. They don't bring any meaning. So it will be much harder, okay, to predict what will be the next token. حتى الآن نحن البشر لو نعطيك مثلا 2 characters ونقول لك what is the next character, very difficult. لكن لو نعطيك 2 words and what is the third word, it will provide more semantic context that will allow you to make better prediction. For the same difficulty that we will face, same thing the self-attention module in the transformer will be facing as well, because the semantic structure will be completely abstracted into the character level tokenization. And one of the most famous example is the Shakespeare dataset. And one of the best guys that do nice tutorials is Karpathy. I recommend you to see Karpathy video lectures on building a GPT-2 from scratch. Okay, and it basically uses the Shakespeare dataset on the GPT-2 transformer architecture that he builds from scratch. And at the end, he shows how you can build an LLM that will predict what is the next character. And of course, at the end, it was an educational example. It didn't yield to something meaningful. Although at the end, it started to predict some correct words. But in a whole, doesn't make a lot of sense, because it's really difficult to predict the next token. Doesn't provide sufficient context details. Okay, and imagine that to be or not to be will be encoded into this vector, which is very difficult to process. Okay. These are just some additional information, but we've talked about all these different limitations. Now, the other extreme, we took one extreme, which is character level tokenization. The other extreme is word level tokenization. And in this case, it's also simple. I will have a sentence or a data set, and I will extract all the unique words into this data set, and every unique word will be considered as a token. So splits the text and individual words, treating each word as a token. So this is better in terms of bringing more semantics. But we will have also, so the vocabulary size will depend on the number of unique words in the data set. and it captures the word level semantics. It's easier to capture semantics between words rather than between characters. And words are meaningful units of text. But of course, it will be pretty much dependent on the language. Okay, if you want to use another language, you need to bring a different data set, and it will bring also different type of words, and this will extend the vocabulary. Now, if you take only the English language, how many unique words we have? You know, a couple of maybe, I don't know, 100,000, you know, maybe millions, I don't know. اللغة العربية في كلمات حتى ما نعرفوها عن الكل. والمشكلة الآن بين الجذور والمشتقات، لو ناخذ من فعل جميع الكلمات الممكن نخرج بحر. فيصبح عندي vocabulary size almost unlimited. Okay, goes to infinity. واللغات تتغير dynamic. But this makes it much more difficult, okay, to control. Okay. So the pros and cons here. Word level tokenization, we consider a single token captures the full meaning. It preserves the semantic unit, and the model can see the complete word. That's a good point. Okay, and it will reduce the number of tokens. Okay, now these two words will bring 2 tokens as compared to character-based tokenization. Okay, 16 tokens for the same sentence. So that's an advantage. And this is if we consider it on the Shakespeare data set. Okay, it will result into a vocabulary size of 30K. Look, 30K only on the Shakespeare data set. You have 30K different words. Now, if we consider the whole English language, you know, we're going to find maybe a couple of millions of unique words. Okay, and this is, you know, if we do word level tokenizer, we're going to, first of all, provide an input text, tokenize the input text into word tokenizers, different words, map every word to the number in the vocabulary. Okay, so this is how we will feed it to the transformer or to the embedding layer, 0, 1 until 5, to represent to be or not to be. And then we will do the embedding and finally provide it to the transformer to be trained or to do an inference. So the advantage, we've talked about them, but the disadvantages, we will have very large vocabulary as already discussed. Okay, only 30K for just one data set from one author. And we will have a lot of out of vocabulary issues. Okay, several words could be unseen. So you can have some example of composed words like this. خاصة في الطب في كلمات القاء متكونة من كلمات أخرى. فإit's difficult. طبعا يمكن في data sets أخرى لكن you will increase even more and more the total possible number of characters. Why we don't want to have very large vocabulary? Computation expansion. أيضا أعطيني confusion في probability. At the end, autoregressive model, if you are going to assign a probability to each possible token. مش لما يكون عندك مليون، مش لما يكون عندك 100,000، مش لما يكون عندك 30,000. فهو it's a balance, it's a hyper parameter, which لأنه فيه يعني توكنايزر غالبا يمشوا من 10,000 إلى 100,000. Okay, and it's a hyper parameter that could have an impact on the performance of the LLM. And it's inefficient for complex languages like German. So German, you can have one word that is composed of 4 words. It solves part of the problem, but not all the problem. Okay, still these challenges are not easy to address when building a language model. But we can use this for simple example. Okay. So it is the word level tokenization is useful for high resource languages where vocabulary and grammar rules are well defined, or for semantic tasks, sentiment analysis. It's pretty much useful because every word will capture the semantics. Okay, topic modeling or text classification, or short text as well, like tweets, caption, and product reviews. So in summary, if the vocabulary could be contained and not large, in this case, we can use word level tokenization. So now we have seen the two extremes, character level, word level, and we have identified their challenges and their benefits. And you want to have something more optimized. And here it comes the subword level tokenization. So the subword level tokenization, it tries to bridge the gap between character and word tokenizers. We have seen the drawbacks of character level: long sequences, limited semantics, efficient attention. And here we have large vocabulary. We can have out of vocabulary problem and inflexible units. So this solves both gaps. So it can make a balanced sequence length. So the sequence length is the hyperparameter that we can try to identify in the beginning, okay, in the tokenizer. I want to build a tokenizer, and it should stop when it reaches 30,000 tokens, or 50,000 tokens, or 100,000 tokens. Okay, and it can capture the subword meaning. صحيح أن الكلمات تعطي معنى أفضل، لكن أيضا حتى الجذور قد تعطي معنى. ولذلك في الأرلي ماشين ليرنينج مودلز مثل ال RNN وال LSTM كان في بري بروسيسنج فيز اللي هي ستيمينج، يشيلوا كل السوابق واللواحق والشكل، يخليه فقط جذور الكلمات ويدخلوها في الترانسفورمر. لأنها مش تعطي معنى عام في السنتمنت اناليسيس، في التكست كلاسيفيكيشن يعطي معنى. لو فقط نعطيك جملة متكونة من جذور كلمات تستطيع تخرج معنى عام، لكن المعاني الخاصة very specific information it's difficult to make text generation. مثلا text generation is more difficult. It doesn't depend only on the roots, okay, ولا on the bare bone language representation, but it depends on all the different characteristics and the morphological structure of the language. And this is why, okay, so it will be also easy, not easy, maybe more challenging for the transformer to capture the meaning by the word, but still feasible, much more feasible than the character level tokenization. So this provides an excellent trade-off between the benefits and the limitations between word tokenization and character level tokenization. And very important thing, it can handle rare words, because some of the words can be a combination of two different tokens. So in this case, I'm able to constitute words out of tokens. And this is why a good tokenizer is the tokenizer that have the ability to capture the morphological structure of a language, okay, such that I can create complete words by combining different tokens. And this combination will be learned by the self-attention module, okay, of course, with a huge amount of text, okay, it will have better convergence on capturing the meaning of these different tokens. And how this is done, so the subword tokenization, it tries to subdivide the words by using prefix recognition, okay, or suffix recognition. And changeable, the good tokenizer will subdivide it into unchangeable, because this can be used, like for example, unconstrained, okay, and changeable, comfortable, you know, it can be a suffix of several other words. So in this case, I will provide 3 tokens instead of 1 token, and this will reduce the vocabulary size, okay. This will reduce the vocabulary size to a good extent, because now instead of having change as a token, unchangeable as a token, okay, change as another token, now I can have change, even D or ED can be a token, so I can combine. And of course the tokenizer optimization will try to find what is the best suffix and what is the best prefix. بعدين لما نشوف performance metrics، من بعض المتركس هو the ability to identify the roots of the words, precision and recall of identifying the roots of the different words, whereas suffix, the suffix precision and recall. Yes.
Doctor, if the sentence has مثلا or has un 5 times, this would be one token, صح?
It has what?
يعني مثلا the un مثلا unchangeable, undefined, whatever.
Okay, undefined, yes. Okay.
UN will be counted as 1 token, صح?
UN will be counted as a 1 token,
That's
yes.
why we will have less vocabulary.
Vice vocabulary, yes. Okay. So basically, when we build a tokenizer, we will start from the characters, and then we will merge the most common pairs. هذه الفكرة متاع البايت بير encoding. And every character is a byte, So I'm going to find what are the two pairs that are likely to be redundant or close to each other most often the time. So it's basically frequency, calculating the frequency of the pairs. And if the two pairs are together most frequently, I will put them as one token. هذه هي الفكرة. فنكبر في الفوكابولري with respect to the character وننقص في الفوكابولري with respect to the word tokenization. لأن الآن لو خرجت هذه لو مثلا عندي undefined, unchanged, so this will be a token, this will be a token. خلاص الآن many words will be deleted because they can be composed. Okay? And at the end, with respect to the character level tokenization, بديت مثلا من 26 مش نوصل ل 100 أو 200 أو 1000 أو 10000. فهمت؟ ف this is why the subword is going to make the balance. Now where to stop? It's hyperparameter. You want to make large, small, and usually أنا we did a tokenizer in Arabic وعملنا different versions من 32K ل 68K. And I will show you some of the evaluations that we've made on these tokenizers.
But doctor, ليش stemming doesn't work with tokenization? It works in NLP بس
You don't need. لأنه ال LLM it will take everything. يعني stemming كان مع to reduce the complexity of the sentence على الماشين learning models.
we don't want to reduce that.
خاصة ما قبل ال RNN وال LSTM. وما استعملوهم حتى مع ال RNN وال LSTM. بعض الأحيان ما يستعملوهمش. It's pre-processing. It depends. If the model is very complex, I mean, if the language is very complex and the model is simplistic, it's better to reduce the complexity of your input. Okay, to provide a better convergence. Like now, since we have large language models, they can capture any kind of relationship. So we have the luxury not to do any pre-processing steps like stemming والأشياء يوم الكل والpunctuation والأشياء يوم الكل. Yes. Okay. Let's look now in Arabic. شوف هذه آية من القرآن الكريم أنلزمكموها وأنتم لها كارهون. شوف ركزوا على كلمة أنلزمكموها. هي كيف ترجمها بالإنجليزية؟ تترجم إلى 4 ولا 5 كلمات. أوكي؟ فيها استفهام. نلزم the root. كم you أنتم. وها okay object pronoun. ف you can see one word in Arabic is composed of different words. So a good tokenizer will be able to understand this kind of look, and this is something very specific to Arabic. Maybe in other languages يكون فيهم different type of combination مثل الألمانية يكون 4 كلمات يخلون في كلمة واحدة. لكن احنا في العربية عندنا structure مختلف وذلك الكومبلكسيتي في العربية تكون أكبر. في ال LLMs شوفوا أنا كل ما NLP عربي صعب جدا إلى الآن وما حققناش تقدم قوي جدا في الموضوع. يعني حتى الآن احنا عندنا من سنة ونص نشتغلوا على language model باللغة العربية and we are facing a lot of difficulties. Our difficulty is the data itself, although we collected a huge amount of data, almost like 1 terabyte of data with a lot of tokens, but still for training a scale LLM you even need more. Yeah. Yes.
When you collect the data, the other data, we do have different so how
Yes. Yeah, we collect every type of data, but sometimes, for example, to train small models, we can be selective. For example, I will say, I'm going to use only news data to train 100 million parameter model. بعدين when we increase the model size, we can add other type of data. ممكن مثلا أضفنا بعض الأحيان الأدب، الشعر، الشريعة، فهمت؟ فهنا we can choose لأنه if your model is small, you cannot put a lot of data. يصبح عندك يمكن overfitting ولا underfitting كل. Usually there is a rule based on the model size, the size of data that will be fitting into the model. فاحنا we use different type of models. Social network model. طبعا social network كان أثر على الجنريشن بعض الأحيان يعطينا باد اوتبوت يعني اللانجوج المستعمل في السوشيال نتورك معناه ما يكونش جيد في بعض الأحيان. ف you can see the impact of your data on the way on the LLM will be trained. ولذلك الآن لو تلاحظوا الديب سيك ما أعرفش كان جربتوا الديب سيك اللي عملوا الصينيين في الأخير. The output is almost GPT-4. And it seems that they have trained their model on the GPT-4 output, which is impressive. And they were able to have a GPT-4-like performance with 96% reduction in the pricing of pre-trained model, which is impressive. And now they have even released 2 days ago the R1 model, which is the reasoning model that was proven to even outperform the O1 model of OpenAI, which is now the game is going to change in the next couple of months. And I think one of the reasons is the quality of data that they have been training their model on. And it's multilingual, it's really impressive. It's the first model, open source model, that impressed me so far, much more better than Llama, all the different versions with different scales, better than Gemini. It's really impressive. So of course now people don't talk anymore about large language model. They are talking about large reasoning model, which is another scale, which is training the model not only to produce tokens, as I'm teaching now, but to reason. And they have integrated the technique, the prompting technique that is called chain of thought, in the pre-training the model and also generated preferences. So this model will try to first think and then respond. Okay, so it's another level of, it's the new era of LLMs right now with advanced reasoning techniques. Inshallah, we will have, when we talk about transformer, I will have like maybe some part discussing the large reasoning model and also the concept of mixture of expert. لأن النماذج اللغوية الكبيرة مثل شات جي بي تي كان يطوروا نموذج large scale all in one. It does everything. Now they found that this is very expensive. So now the other technique is that they train smaller models, and every model will be very specific to particular tasks. And when you provide the prompt, you want to write a coding, they will send it to a coding expert, and you don't know. So there should be kind of a router based on the question, and they can send it to one expert model or multiple expert model, and they will collaborate to provide you the output. Okay, and now they are even doing more advances to include reasoning besides the token generation. Okay. So this is a very, very dynamic, maybe next year if we teach this course, we're going to teach it in a different way because maybe these things will be deprecated. But still, these are the foundation. I mean, everyone, if you want to do a large reasoning model, you need to understand tokenization, embedding models is like the ground for anything else that will come afterwards. And now you can see that these complex type of Arabic words, they require pattern recognition. So there is a particular pattern here, okay? And this pattern, you cannot find it probably in other type of languages, okay? There is a semantic clarity. Each subword carries a distinct grammatical and semantic meaning here. So if we consider these are different tokens, okay? Of course, with the larger scale of the data that we can train a transformer on, it can understand that this could have an interrogative meaning, this can have an object pronoun meaning, okay? But, this is based on the quality and the quantity of data that we'll be using to train a transformer on. Okay. Of course, so this was just to trigger the importance of thinking that we need to bring this type of words into more meaningful subwords and identify common patterns. At the end, what a language model do is pattern recognition to make better inference. This is like the standard rule in machine learning to identify patterns. So instead of identifying patterns at word level, we try to identify patterns into subword level. Of course, it's more challenging, more complex, but with the quantity of data, with now abundant resources that people can have to pre-train their model, this pattern recognition becomes possible. These are some other examples, okay, starting from root and different variations of a possible word in Arabic language as well. Okay, now I think we have agreed there is a need to have subword tokenization technique that will efficiently subdivide a word into tokens. And the most popular techniques, and we will cover two of them today, the byte pair encoding, the BPE, and this is what OpenAI they have proposed and they have used in their paper, first paper GPT-2. It merges frequently co-occurring character sequences. So the idea is simple. If I have a word like this, I'm going to consider each character alone, and then I will check which characters can occur with each other. For example, after reading a lot of English text, we can understand that an is repeated as a prefix for many other words. طبعا هذا مثل ما نتعلموا احنا لما نقرأه الإنجليزية في الأول ممكن تمر عليك الكلمة ما تلقيش لها بال، لكن لما تتكرر أمامك العديد من المرات تكتشف فيه الباترن. فالآن هذه قبل الهابينس ما جتش فقط في الكلمة هذه. It has repeated over so many other words. So you know now there is a pattern. Okay? في other pattern IN, incomplete, inconsistent. But we know that IN can have a problem that opposite of what the word meaning would like to do. Okay? So, and this will only be understandable by the LLM only when it reads during the pre-training phase. And in the pre-training phase, the objective is to learn the language. While fine-tuning phase is to learn the skills. فأنا دائما نشبه نقول pre-training phase عبارة عن شخص he will go to abroad, another country, so he need to spend 1 year or 2 years learning the language. يتعلم ألمانية، يتعلم إيطالية، يتعلم إنجليزية. ثم يدخل الجامعة يتعلم مهارات. دخول الجامعة يسمى فاين تيونينج. الآن خلاص مش نسخ المهارات اللي عنده مش هنرجع ميكانيكال انجينيرنج ولا ميديكال ولا أي شيء. هذوما مهارات تعلمها. لكن في الأول لازم يتعلم لغة. He knows how to express the language. And this is what we do when we pre-train a model is we teach them the language or the languages if it is a multilingual model. And the language, it means capturing these different type of patterns. And this is why I repeated several times, the tokenizer will provide the ground. If you have bad tokenizer, you will make confusing. تخيل انت لغة ما فيها ولا pattern. الآن لما ننظر اللغة الصينية تقول هذه مستحيل نتعلمها. لماذا؟ You are not able to capture any pattern. لكن لما تركز وتقرأ كثير you will find patterns يسمح لك تقرأ الكلمات. Okay, so pattern recognition is the key here, and the tokenizer will pave the way to make this pattern recognition easier and faster. Okay, so SentencePiece, it will do the same thing. It basically uses BPE, but instead of considering character sequence, it will consider Unicode byte. Okay, instead of character sequence, and I will show you the difference. And WordPiece, it will build vocabulary based on token frequency. Okay. So let's start by the byte pair encoding. Definition. So the idea is very simple. It's a text compression algorithm. So it will compress the text. It will reduce the vocabulary of a particular corpus, so it can be manageable using NLP to balance the sequence length and the vocabulary size. Sequence length تكون طويلة في character based tokenization, and vocabulary size is huge in word based tokenization, so it will make the balance between both. And how it works, it will start, so it will consider a complete text as a sequence of characters, and then it will try to merge. So imagine that you have a sequence of characters like this. This is the first step. You can observe that I have a pattern A, and it's repeated again here. So I can consider, I will create a new token, I will call it capital Z, and capital Z will be mapped to AA. So I will replace 2 tokens with 1 token, because I have a frequency of 2, so I create a token Z. So what happens? This sequence will be written as ZA. نفس الشيء. I will replace Z where there is AA. فايش عملت الآن؟ نقصنا في السيكونس لينث. اوكي؟ وكبرنا في الفوكابولري. شوف الفوكابولري كم بدأت منه هنا؟ عندي 1 2 3 4. I have 4 characters الفوكابولري. كم أصبح عندي هنا؟ 1 2 3 4 5. الفوكابولري increased and the sequence decreased. The vocabulary size increased and the sequence length decreased. Okay, and the sequence length أكبر من هذه. I can represent this sentence in smaller number of tokens because I have merged. ركزوا معي في المثال هذا لأنه إذا فهمت هذا تفهم الباقي كامل. This is like a mechanical example to understand. Now we will do the same thing. We will do another iteration. What are the two tokens that will repeat? And the AB, AB. Frequency 2, I will create another token. يصير الآن. So this sequence will be represented into this sequence. ZY هنا ZY يعني عندي ال AB هذه غيرتها بالواي. فالفوكابلري أصبح عندي الآن 1 2 3 4 5 اللي قاعدوا نفسه لأن البي دخلت. أوكي. لكن I have smaller sequence. شوف السيكونس كم كانت فيها هذه الآن يمكن فيها 10 الآن فيها أقل. لا احنا في الأول أخذنا ال A هذه. which B؟ لا احنا ناخذ pair. It's byte pair encoding pair. Byte pair. Okay, so you take only pair. Okay, pair by pair, and you do this at every iteration. الiteration هذا سميه merging. When you change a pair of token with one token, this is the merging step. Okay, عملنا combination. And we do the same thing. شوف الآن merge token they can be merged. شو عندي الآن ZY هما أصلا merged من قبل. فممكن نغير ZY هذه X تصبح عندي XD XAC. هذه عملية الانكودينج. I encode it with new tokens. الديكودينج لازم نرجع بالعكس. بشوف الإكس هذا it's a complex, it's a composed token متكون من composite Y Z وهذا لازم نعمل له decoding باش نرجع للسيكونس الأصلية. واضح؟ So this process is going to repeat until you reach your desired vocabulary size. لأنه أنت توكنايزر تقول في الأخير نحب يكون عندي 30,000 كلمة. Okay, 30,000 tokens. You can specify the size of your token vocabulary, and based on this, you're going to do merges over several iterations until you reach this number. And at the end, this is you're going to have the final vocabulary: X equal ZY, Y equal AB, and Z equal AA. This is our vocabulary. هذا الآن متكون from 3 tokens. وطبعا they refer to other tokens after the merges that we have done. فالآن I can compose a sentence like this using these tokens. فالأخير if you enroll these tokens you'll have exactly the same thing. لكن the way to represent them is smaller. فانتقلنا من الكاركتر based إلى السبورد based. اوكي وربحنا في مسألة sequence length أصبحت أقل وزدنا بعض التوكنز في الفوكابولري. اوكي طبعا ال A will be they are still part of the language. اوكي فالآن أصبح النمبر of tokens عندي A B C وزيد عليهم Z والY والX. كان عندي 4 أصبح عندي 7. فهذاك علاش vocabulary size باش يكبر مقارنة مع الكاركتر. And we can do, of course, with very large corpus, you can do several merges until you reach a certain desired vocabulary size. هذا مبدأ العام. So this is the main concept of the byte pair encoding intuition. And now let's see how we can do this in practice. So this is the algorithm that you need to follow. You initialize, you have to parse the input sequence S and define the initial vocabulary V, okay? And then you identify the most frequent pair of consecutive tokens. Create a new token for every frequent pair, and replace it, okay, within the corpus with, or in the vocabulary with TNew. Okay, and this will result into a new sequence S prime and a vocabulary V. So vocabulary V يبدا initially من الكاركترز وبعدين يزيدوا عليه من الكومبينيشنز الميرجز هذوما الكل اللي هم يعتبروا التوكنز subwords. ففي الأخير we expect a good tokenizer. It will extract the root of the verbs. It will extract the prefixes, the suffixes, the punctuations, the things that should be. It's like a clustering of characters. Okay, and it's unsupervised. Okay, unlabeled. It's going to learn as it goes. It's like clustering technique of different words.
Doctor, do you have already models that does this for us?
موجودين ال BPE can train it. احنا we will build the PPE from scratch. Okay, but there are libraries. SentencePiece نفس الشيء. Okay, you can do that. Okay, so this is a pseudocode of the algorithm. So first of all, we start from a text, and we will encode the text because we will use UTF-8 encoding. So you have lowest, it will be converted into tokens. So BPE, it will work on the UTF-8 coding in the beginning. Okay, so based on this, how do you apply the theorem? Just only look at the first part here. What tokens, pair of tokens are 108 111. Okay, so we come here to get statistics. Well, I find the most common tokens or pair of tokens. Okay, using Python here for X, Y in the different IDs. So these are the IDs. Okay, you will count the number of pairs. Okay, so this will get the statistics. Okay, equal counts dot get XY pair. Okay, plus 1. It will increase. If it doesn't exist 0, or if it exists, it's going to increment it. So this will return pair. This one, it's 2 frequency, and you have 111, 119 also. It's repeating. Okay, let's look. We can take this one. So we will do a merge. 108, 111 will be merged to a new token 256. And this will be mapped to a token 257. طبعا احنا الان نشتغل على UTF-8 يعني the maximum value is 255. فالان we're gonna go a new type of tokens here. Look, so we replace 256 if we make this merge, and then we have 256 and 119. It's repeated also, second iteration. So I will replace this one and this one by 257 and 257. Okay, this is the merge. Okay, it's going to do the merge of every 2 pair of tokens. Okay, for every 2 pair of tokens, it will do the merge of the new ID. And so we need to do this operation and this operation multiple times. And for this, we can create the BPE algorithm, which will loop over. It will create the tokens, which is this one, convert the text into a list of numbers, and then the vocabulary will be the initial tokens. This is our vocabulary. And then it will loop over get statistics and also merging the tokens several times until I reach the vocabulary size that I want to reach. هذه الفكرة الأساسية. طبعا this is a simple pseudocode like an implementation. There are different ways on how you can do the implementation. Yes.
But the merging happens per text, so each text will have different merging.
It's pair of bytes. اسمعنا. This is 1 byte, and this is 1 byte, and it's repeating 2 times. So I will take these 2 bytes and change them with 1 number.
So whenever it comes in different text, 108 and 111, it will merge the same number as the same text.
Yes. في كل الكوربس تغيره.
So it will be text for all.
نعم. فأنت الآن مثلا لو تعمل if you want a vocabulary size of 30,000 tokens, you will have indices from 0 to 30,000 minus 1. فالعدد الكل يكون 30,000 tokens. يمكن يكون plus minus، لكن في الأخير you will have indices from 0 to around 30,000. وكل index it will be mapped to a token.
I do have a question. مثلا هنا we have to 256 which is representing 108 111.
Yes.
So maybe يعني in another text we will have the same number as a word, not as يعني these two pocket يعني اقصد انه ممكن يجيني 256 كذا فهو راح يفهم.
لا الآن we don't care. الآن من اللي حولنا لليو تي اف 8 تحولت الأمور، أصبح بعدين الباترن ريكوجنيشن في الألجوريثم باش يشوف الفريكونسي. شوف الآن عندنا سبيس هنا.
صح.
إيه إذا تكرر سبيس يمكن يدخلوا. الآن هو دخلوا في 257 it was a space. Okay. In this case it's W. 119 it's about the W here. Now when you convert to these numbers, which is the initial vocabulary IDs, you will do the merge based on this. You know, the BPE is going to discover in an unsupervised manner the morphological structure of the language.
ما راح يصير في أي confusion يعني.
قد يكون. So لا في optimizations. أنا طبعا بعدين نوريك هذا standard BPE. لكن الأوبن AI when they implemented BPE they made optimization to make it even better. This is the standard. It will do some job, but of course it could have some limitations. لكن من حيث المبدأ it's much better than what we had before اللي هو character based ولا الword based tokenization. طبعا البرسنتج اوف ايرور يكون اعظم لما اللانجوجز يكونوا very complex. لما تعمل مالتي لينجوال وفي عندك many special characters you will have a lot of confusion here. It's not going to work out of the box. حتى في الانجليش لانجوج بوريكم الان الاوبتمايزيشن تكنيك اللي عملوه اوبن اي اي to avoid some weird circumstances. We will discuss this later. But now this is just an introduction to the standard algorithm. There are so many optimizations that we can do. It will do a pretty much good job into identifying the most important morphological structure and semantic structure of the language to a good extent. طبعا الاوتبوت شفت نفس الالجوريثم it will provide you completely different output if you provide different data sets. This is data set driven. إذا data set فيها much noise it will have bad convergence. إذا التكست clean يعطيك نتائج يكون أفضل. واضحة؟ I will show you optimization, but now from the principle this algorithm is intuitive, okay, in terms of merging the most frequent words. لأنه في الأخير الروتس باش يكونوا frequent مع بعض والprefixes باش يكونوا frequent والprefixes والsuffixes يكونوا في هذا في التصور العام. لكن الداتا set it can lead to bad performance. مشكلة probably not in the algorithm itself but in the data set. So optimization could be made based on the complexity of the data set that you provide. If you apply this only on English, pure clean English language, it can be sufficient. لو ندخل عليه other languages, لو ندخل عليه social media input, it's completely معناها not clean. So we will have more issues. فلذلك يعني optimization we think about them based on the output. So you can train the first version, it's not, and you will see some performance metrics. There are some performance metrics اللي يعطيوك مثلا الروت identification percentage. فإذا كان الروت identification percentage is low, it means it has issues in detecting the correct morphological structure of the language. So probably I need to do some different type of techniques. لكن BPE as a protocol, it's like the standard approach for identifying these relationships. ما نعرف جاوبت على سؤالك ولا؟ Okay. Okay, let's stop here. Now it's a good time to stop this to digest this, and then we will continue into the implementation details. بسم الله الرحمن الرحيم. والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so now we have introduced, and I hope you understood the main concept of byte pair encoding. It's basically clustering the pair of bytes that recur so often, more frequent. And let's move forward. Okay, so what I presented is the general byte pair encoding technique. And this was the algorithm used for the tokenization of GPT-2 back in 2019. And this is the paper. Language models are unsupervised multitask learner. And this is the paper back in 2019, which introduced GPT-2. At that point, the largest model of OpenAI, 1.5 billion, until they released GPT 3.5 at 175 billion parameters. So almost 100 times more than the GPT-2. And our interest here in the GPT-2 paper is in the tokenization part. And let's read it together. And here, so the byte pair encoding is a practical, and it was proposed in 2015. It's practical middle ground between character and word level language modeling, which we have introduced today, which effectively interpolate between word level inputs for frequent symbols sequences and character level inputs for infrequent symbol sequences. And despite its name, reference BPE implementation often operate on Unicode code points and not on byte sequences. And you know, what they say here, it actually applies to SentencePiece that was proposed by Google, which we are going to introduce. And it operates on Unicode points and not on byte level. So here BPE will be applied on byte level implementation, the same that we have introduced. And this implementation would require including the full space of Unicode symbols in order to model all Unicode strings. Okay, and here this would result in base vocabulary over 130. Yeah, here it talks about the Unicode tokenization that we talked about. And look, at that time it has 130,000 characters, the Unicode character schema, which is not efficient, before any multi-symbol token are added. Okay, and they said here this is very large compared to 32K or 64K token vocabularies often used with BPE. Okay, so here it defines BPE in the same way. We already went through the Unicode possible tokenization, character level tokenization, word level tokenization. Were you able to understand this passage of the paper or not? Does this make sense? Yeah, it just introduced BPE. It says it's something in between character level tokenization and word level tokenization. It makes an interpolation between both. Okay, it tried to find the frequent symbol sequences, and this is what we have introduced. And then it says that Unicode tokenization is not appropriate because of the size, and this is what I presented first, if you remember. And we said that Unicode is dynamic, it has a very large vocabulary size, and it's based on like character-based tokenization, which is not sufficient. And it says that BPE can provide more compressed vocabularies of 32K or 64K tokens. And this is what they have used here. Okay. However, applying BPE in the same way that I presented before to byte sequence result in suboptimal merges due to BPE using a greedy frequency-based heuristic for building the token vocabulary. وهذه النقطة اللي كنا نتكلموا فيها من قبل أنه في optimization techniques when we want to use BPE into some specific circumstances, like for example building LLMs, like here in this case GPT-2. فالاشكال البي بي اي مش يركز فقط على الفريكونسي، ما هوش ياخذ في الاعتبار اي شيء اخر. فلذلك when the language is very complex and there are several like awkward words, it may result to suboptimal solutions. وطبعا هذول الاشياء يكونوا غالبا based on observation. ممكن they try to run BPE and they find suboptimal solutions. And here they come up قال we observed BPE including many variation of common word like dog and dog like this. So BPE is going to provide you dog with a dot, dog with an exclamation mark and dog with interrogation mark like this. هذا البي بي اي ستاندرد لو نستعملوه باش يعطينا هذوما 3 tokens. What would be preferred? It will be preferred to have dog and these punctuations as other tokens. هو لأنه متكرروا أمامه هو شي يركز على التكرار. إذا عندي داتا سيت هذو متكررين بكثرة مش يعمل ميرج. فسب اوبتيمال. هذا based on observation. Okay, you cannot anticipate into this because this depends also on the data set used. So this results into a suboptimal allocation of limited vocabulary slot and model capacity. To avoid this, we prevent BPE from merging across character categories for any byte sequence. We add an exception for spaces, which significantly improves the compression efficiency while adding only minimal fragmentation of words across multiple vocabulary. هذا نشوفوا الطريقة كيف سووهم. Okay, so BPE for GPT-2, it handles Unicode string efficiently and overcomes the limitation of traditional tokenization methods, اللي هم الكاركتر والword, and provides an optimal tokenization by compressing frequent word patterns, أيضا managing the rare characters sequences. Okay, so here in this case, it will prevent using some regular expression that these words will be tokenized or merged together. So this dog and, for example, exclamation mark will not be merged. And they do this using predefined conditions. So let me take you to their code. This is from GitHub of GPT-2 tokenizer. You can write GPT-2 GitHub and you go to, I think, a script that is called encoder.py. You will find this one. Okay, so get pairs. This is statistics that it collect the pairs. So it's the same that we have used. And here, in their encoder, which will actually run the BPE algorithm, they made a regular expression such that to prevent merges that can happen for capitalized version of okay, so this is a regular expression. Of course, this is not easy to understand, but this basically will prevent to merge some words with some special characters, okay, without going into all the details of this complex regular expression. And just to get an intuition about the regular expression, okay, the output of the regular expression, imagine that you provide a sentence like this, and look, I've put several spaces, and I have put these two question mark and exclamation mark. And when I apply this regular expression, it uses regx, which is a library in Python, to define a regular expression. And when we try to find all sequences based on this regular expression, is going to tokenize it in this way. Okay, so it will take this is with a space, example with a space here, GPT-2, but look, it put this exclamation mark out, okay, not concatenated to the words. It didn't make any merge here. So by applying this in the BPE algorithm, okay, it will be able to separate special characters from particular words, and this will prevent, so they have added a precondition before doing the tokenization. Okay, so what they do, they will have a corpus, they will separate it, apply this filter, and then they will tokenize every word, and then they will do the concatenation back. And in this way, they provided much better efficiency in terms of compression and also efficiency of the tokenization. And look now, for example, even these multiple spaces, they were not appended all of them to the input, but they will be separate from.
Doctor,
Yeah.
why did you take both the question mark and exclamation mark together? Not
Yeah.
separate one?
I mean, because this can be merged if they occur several times, but the most important thing is that we avoid for these to happen into words, you know, so we don't have different variations of the same word. Okay. And here there is a bit more explanation about the regular expression. So this part, which is this one, it matches common English words. Okay, so it will extract common English words. This part, it matches sequence of letters, Unicode properties, and this match sequence of numbers. This match special characters, and match trailing white space. Of course, this type of regular expression is not very intuitive, but it's a very powerful means in order to identify patterns in certain context. And let's look here in this example. Okay, so here I applied the same filter on a sample code. This is the Python script. And we can observe that this filter, or this regular expression, was able to properly, okay, tokenize this script in a proper way. So, and this gives almost the same, okay, it gives the same way in the tick tokenizer graphical interface. So this is the same script here. Okay, when we use the regular expression, is going to separate the words from the special characters, and then these special characters will be later on tokenized, and finally it will result into the following tokenization using the GPT-2, and this will lead to 228 tokens. Of course, GPT tokenizer is not efficient, as we have already introduced in the beginning. Then there was another variant of GPT-4 that actually accounted much better for the different spaces in coding script. To work with tokenizers with OpenAI, there is a famous library that is called Tick Token from OpenAI, which you can import in Python. It's used for GPT-2, GPT-3, and GPT-4 and other OpenAI models. And it implements the byte pair encoding for efficient tokenization. Okay. So let's see what is the key differences between GPT-2 and GPT-4. So GPT-2, it uses case-sensitive regular expression, so the same regular expression that we have introduced. And GPT-4, it uses case and sensitive regular expression. So GPT-4, it will consider, capital letter and non-capital letter as the same thing. So it will ignore sensitive cases. It will handle the number up to 3 digits. So it will make a clustering, and we have seen this in the beginning when we compared the arithmetic operations with GPT-2 tokenizer and GPT-4 tokenizer. Okay, so it will take 1, 2, 3, but it will not make clustering of 4 digits together. And they use a different type of regular expression. So GPT-4 has better handling of white spaces. They are merged for better compression, especially in coding. For the vocabulary size, so GPT-4 has 100,000 tokens. It's larger vocabulary for better coverage, of course, because it's much larger model. Okay, with multilingual, it considers different type of languages, different type of tasks. So this is why the vocabulary size is much higher. So maybe the general recommendation is that when your model is very large, your vocabulary should be also larger, because the self-attention module, especially with a huge amount of data, it will be able to learn the dependencies between larger number of tokens. But if you have a small model, it means you have smaller number of layers. You will not have sufficient layers to extract all the different features and patterns from this from a very large corpus. So there is a dependency between the scale of the vocabulary and the scale of the LLM model. There is no clear rule, but they are kind of proportional, or not really proportional. There should be some relationship, not necessarily linear. Okay, special tokens. So GPT-4 add more special tokens for better understanding of, and I'm going to introduce special tokens. And this is just a summary. So these changes, they have dramatically improved the performance of GPT-4 models. Of course, not only this, but also other considerations, because better handling of case sensitivity, more efficient white space merging, and prevents overly long number of sequences by merging spaces, for example, and better generalization. Okay, and these slides just summarizes the different differences that we've talked about. And this is the result, comparison of tokenization of a Python script as we already introduced. So based on these techniques, instead of accounting for this indentation as multiple spaces, so only one space is considered. And this result, for example, look, it's almost the half. The same Python script is encoded into 100 tokens as compared to 200 tokens. So the self-attention module will have a much better ability to learn. And if you have used GPT, okay, probably 3.4, 3.5 before and 4, there is big difference in terms of generation, in terms of understanding. And of course, GPT-2 is not like that reliable model. I mean, it's able to do generations, but it's not as sophisticated as 3.5 and 4. And tokenization was one of the techniques that has been improved and that have dramatically changed the performance of the algorithms. I mean, now, if you use GPT-4 with the old tokenization technique of GPT-2, it's impossible that you get the same performance and the same accuracy that we are getting with this tokenizer. Voila. Okay? Because finding dependencies with smaller number of tokens is easier than finding the dependencies by more number of tokens. Yes?
If we have more vocabulary, does it mean that we will have a more efficient response? The response will be قصير ومرة accurate. وين ما يدخل؟
It is a hyperparameter. يعني الآن the vocabulary of GPT-4 tokenizer is bigger because the model is bigger. So as already explained, it has more ability to detect patterns with longer context. The vocabulary size will impact on the context length, will impact on the model size, because at the end your model should be able to discern the features and the patterns that are underlying between these tokens. Okay. And look now for tokenization for Arabic script. Look at the difference. So not much difference, but still, and this is just a small sentence, 136 as compared to 99. It means that it's able to recognize better the morphology of the Arabic context by grouping the tokens that are probably more frequent to be related. Let's look here. So we have, this is almost the same. Okay. شوف ال التعريفية it's one token. نفس الشيء هنا. Okay. But still, okay, can we find, شوف هنا مثلا إنما جت في أول الكلمة tokenization مختلفة على لما جت في وسط الكلمة. And this is something common as well. Okay. لأن الجروبينج في أول كلمة قد يكون مختلف عن الجروبينج في آخرها. رسول. اوكي هنا ما استطاعش يجمع كلمة رسول مع بعض. إيه. still you can see it's less efficient in the Arabic context. معناها الآن اللي يمكن نستنتج أن التوكنايزر هذا was not able to find the roots of the Arabic corpus. أي وهذاك علاش الآن الكواليتي اوف جنريشن في العربي أقل بكثير بالنسبة للجي بي تي 4 كواليتي اوف جنريشن للإنجليش. الجي بي تي 4 او أفضل بكثير من جي بي تي 4 في الأرابيك جنريشن. فأنا I didn't check now the GPT-4 O tokenizer, but I think it should be different from the GPT-4 نفسه. أصلا الآن GPT-4 is deprecated يعني is no longer supported as before. طبعا GPT-4 O أسرع وأدق من GPT-4. لكن في reasoning GPT-4 still has very good reasoning especially in English. Okay. And this is a simple usage of the tick token in Python. So you need to import it. Import tick token. You provide a sample text. Huh? هذه library from OpenAI that allows you to tokenize a sentence. Okay, you can import it, create a sentence, and then create an encoder. So you can create a GPT-2 encoder اللي هو البي بي اي الفيرجن الاولى اللي شفناها. GPT-2 token encoder tick token dot get encoding GPT-2. So this will give you an encoder, and then you use this encoder to encode the text. So this will convert the text into the following tokens. Okay, شوف الآن we have 228 tokens for this text. We do the same thing to create a GPT-4 encoder, and this will give us, say, with encoding CL100K base, and this is going to give the following token. For so the shape will be 111, the half. Okay, so this tokenization is more efficient. في أيضا special token consideration that are defined in GPT-2 and GPT-4 in particular. فالسبيشال توكن نستعملوهم غالبا لما يكون عندنا الشات مودلز، مش فقط تكست كومبليشن لكن شات مودلز. خلينا نمشي المثال مثلا في GPT 3.5 and GPT 4. So usually when you want to send a message to GPT 3, it should go through this structure. You have to send a system message and a user message. A user message هو prompt. This is your question. So even when you write a question on ChatGPT, behind the scene is going to send the following message, a system message that is written by ChatGPT, and then your message that will be the request to the language model. In order to be able to fine-tune these models, we need also to define these special characters in the pre-training phase, so they have to be included in the tokenization as well. So they are later on recognized when I want to fine-tune the model to perform specific tasks. هذول يسميهم special tokens. ما هماش part of the vocabulary. ما تحصلهمش موجودين. مستحيل مثلا تلقى في context أو نادر جدا مش تلقى توكن مثل هذا بالضبط. فهذول special token يقع صناعتهم بطريقة معينة. So later on we can use them to identify. هذا الآن لما تعمل text generation, you need to tell the LLM when to stop. ولا مش يقعد هو دائما عنده next token. فاحنا ندربه ونقول له اذا بديت الجنريشن، اذا جاك التوكن هذا اللي هو الاند، خلاص توقف الجنريشن. فthis token will be used as part to know when to start and when to stop. فلذلك if you do fine tuning without these tokens, you may end up by just keep generating without any end. But this is important, okay, and this type of tokens depend from one model to another. So I put several slides now because of we are almost reaching the time. I'm going to skip them, but this is the implementation of the tokenizer in this is for GPT-4 and this is for GPT-2. So you can find GPT-2 define one special token, which is the end of text, because GPT-2 is a text generation. So I need to tell when to stop. It can be fine-tuned, but it's mainly for knowing the end of text token. And GPT-4 defined more tokens like end of text, theme prefix, the middle, suffix, and end of the prompt. And these are used for fine-tuning purposes. Okay, SentencePiece is basically the same as BPE. The main difference is that SentencePiece will consider code point level instead of byte level processing in BPE. So in BPE, usually when you have a text, you're going to encode it into UTF-8. And then we will consider the sequence of bytes. Okay, it will represent bytes like this, either in hexa or in decimal. So here in code point level processing is going just to read the binary data directly from the file, okay, direct Unicode prints. And for example, this emoji is going to result into 1 code point instead of 4 bytes of UTF-8. So the way on how the characters are represented is different in SentencePiece. Instead of using byte level, it will use code point level. Okay, it works with Unicode characters as single units. Even if they are encoded into several bytes, it will consider as single units. So here we have 5 characters, we have 5 code points. Okay, and look, this is 4 bytes for BPE. It will be considered as 1 code point for SentencePiece. This is one of the main differences between both, but later on, SentencePiece is going to use BPE in order to pre-train tokenizer. These are examples on how to use SentencePiece. So you can install it in Python, you can import it, and then you need to load a pre-trained tokenizer, or you can train your tokenizer. There is a way on how to train a tokenizer with SentencePiece, but this example just shows how this tokenizer was pre-trained for Llama. So you can load it, and you can use it to convert a sentence, hello, I am an assistant, into tokens, and their corresponding token IDs. Okay, it's a library that allows you to do tokenization. And you can do it also by transformer. I think probably some of you know about the transformer library. It has several types of tokenizers that are pre-trained. You can download them, like the OpenLM research / OpenLlama 3 billion. It will download the tokenizer of Llama 3 billion, and then same thing, you provide a text, it's going to provide the tokens and their corresponding token ID. Let's finish in 5 minutes and introduce you the tokenization performance metrics. Now imagine you understand everything, you have your data set, you know how to train a BPE tokenizer or maybe SentencePiece of tokenizer, and you want to know, is my tokenizer efficient? So there are several metrics. I have selected probably 5 of them, but there are others. And the first one is called fertility. Fertility, it measures the average number of tokens per word. Okay? Here, for example, fertility is total number of tokens divided by total number of words. So it gives you an average. الآن مثلا هذا, so this is a SentencePiece 32K tokenizer. It has an average number of tokens 1.2, almost 1.2 token per word. كل كلمة تتكون من 1.2 tokens, okay? Number of tokens per word. كلمة مثلا يعني almost كل كلمة token. هذا الافريج. Okay? هنا almost كل كلمة token. So this is a Aranizer. It's a tokenizer that we've trained in my lab based on a big corpus of data that we collected using BPE and SentencePiece. نفس الطرق استعملناها من البرجز والاشياء اشتغلوا عليها الشباب. And they made different variations. 4 variations of BPE from 32K to 68K. و 4 variations of SentencePiece نفس الشيء. طبعا عملنا different versions لانه when we grow in the model size of LLM we will use bigger models of number of tokens. اوكي الان لما يكون عندك high fertility rate implies that the words are typically split into more subtokens. Very low fertility rate like in our case words are less frequently divided, suggesting a more holistic approach. يعني احنا هون قريبين نوعا ما للword level tokenization. So it's kind of it's fine. يعني الفكرة انه التوكن is 0.75 يعني we are within range غالبا حتى مع other tokenizers اللي في الانجلش language. Another performance metric is the single word token performance. And the definition is the percentage of words that are kept as whole tokens. اللي ما تقسموش. في كلمات ما تقسمتش. فناخذ percentage. Okay. Number of whole words divided by total number of words. يعني التوكن هو كلمة ما تقسمش. يمكن يكون عندك جذر كلمات كرر كثير مرات بقى هو توكن ما تقسمش الكلمة هذه. فهير you can find based on the tokenizer size. Here we have 25% against 18%. And this is logical. لأنه هنا we have increased the vocabulary size. So many words will be divided more and more. فممكن نقولها في الكوربس اللي عندنا في 25% من الكلمات يمكن يكونوا root words والبقية متفرعين. And when you increase the size of the tokenizer vocabulary, you will have smaller single word token. Okay? And here, why it matters? So higher percentage indicates the tokenizer is better preserving the whole words, and lower percentage indicates that tokenizer frequently splits words into subwords. في أيضا الأفريج token length. كم طول كم من character. The average number of characters per token. So here, based on the results, the average goes from 4.88 characters to 5.3 characters. في اللغة العربية في التوكنايزر اللي دربناه. طبعا more tokens it means longer sequences. Okay, and this is coarse granularity. ولا fine granularity you try to subdivide better. فهذوما يعطيوك فكرة على طريقة أداء توكنايزر من from different perspective. Root token performance. The ability of a tokenizer to correctly identify and preserve the root form. مثلا running, it can identify the root of the token. Okay, so look here, 51% in 32K, but higher percentage in 68K. So the bigger vocabulary was able to preserve or identify the roots لأنه استطاع يعمل تقسيم الكلمات فالجذور خرجت بطريقة أنسب. Does it make sense? Suffix precision. في عندنا suffix والprefix. Okay, it's the ability or the accuracy of the tokenizer in correctly identifying suffixes into the word. Okay, أنا طبعا عنده علاقة بالروت يعني 68K was able to identify better لأنه تم التقسيم على أساس الأصول هذه. وطبعا تعرفوا الفرق بين البريسيجن والريكول. So we can also measure the recall. Recall هنا نازل نوعا ما يعني only it was able to recall only 21% of the suffixes among the total actual suffixes available. And this is just a summarization of the different performance metrics in one slide. Okay. Yeah, that's it for today. I hope that you got global information about tokenization and you understood in some of the ways its importance in designing accurate and precise large language models. So next week we'll talk about embedding.